Hello and welcome. We live in a world that's just full of noise, both literally and figuratively. So today, we're going to dive into something pretty amazing, how we can pull a crystal clear signal out of all that random chaos. It's one of the most powerful tools in digital signal processing, and we're going to break down how it all works.
And really think about it for a second. Have you ever wondered how this stuff is even possible? You're on a call, walking down a super windy street, but somehow the person you're talking to hears you, not the wind. Or you're watching a classic old movie, and all that fuzzy grain is just gone. It feels like some kind of magic, right?
Well, it's not magic. It's an incredible piece of engineering called an optimum filter. Think of it like a digital detective, and its one and only job is to solve the mystery of the hidden signal. In this explainer, we're going to pull back the curtain and see exactly how this detective does its job. Okay, so first things first, we have to really get a handle on the core problem here. In just about every kind of communication or data processing you can think of, the pure, clean information we actually want is all mixed up with a bunch of random junk we don't. And that is the fundamental challenge.
Now, the key phrase on this slide is a statistical viewpoint. This is so important. It tells us we're not just taking wild guesses or trying stuff at random. No, the entire approach is built on the solid science of probability and statistics to find what is provably the best way to clean up a signal. So that leads to a really good question. If we're searching for the optimum, the absolute best filter, how on earth do we define what best even means? We can't just eyeball it. We need a target, a clear way to measure our success. And that target has a name, minimum mean square error, or MMSE for short. I know, it sounds a little intimidating, but the idea behind it is actually super simple. All we're trying to do is make the average mistake, the difference between the perfect signal we wish we had and the one our filter gives us, as tiny as humanly possible. The smaller that error, the better our filter is doing its job. And this, right here, this is the whole game plan, laid out in 3 simple steps. First, we decide to use a specific kind of tool, a linear filter. That just means it's predictable and plays by the rules. Second, we use that MMSC idea to measure our errors. And third, we bring in the math to tweak and adjust that filter until the average mistake is as close to 0 as it can possibly get. It's simple, it's elegant, and it's incredibly powerful. All right, so to actually do all this, we need to understand the signals we're dealing with. And this is where a really mind-blowing idea comes into play. It turns out you don't need to predict the future of a signal. You just need to know its statistical recipe. That's right, a secret recipe. Any of these random signals, like the consistent hiss on an old tape or the steady static in a radio signal, can be thought of as having a unique recipe that created it. It's what gives the noise its specific character. And this recipe really only has 2 main ingredients. You start with pure, totally unpredictable white noise. That's your raw material. Then you run that noise through a special kind of filter, what's called a causal filter, which just means it only uses information from the past. And that filter acts like the shaping instructions. It molds that random noise into the specific signal we're trying to understand. So here's the big takeaway. By figuring out this recipe, we don't need to know every single little random thing the signal is going to do next. We just need to know its second-order statistics, which is just a fancy way of saying we need its predictable habits, like its average power and how its values relate to each other over time. We don't need a crystal ball, just a good understanding of its habits. Okay, so we've got the theory down. Now let's see how it gets put to work in one of its most incredible applications, something called linear prediction. This is where that digital detective really starts to show off its skills. Just look at all these places where this stuff works its magic. The filter basically learns the predictable rhythm of the signal it wants to keep, like your voice. By predicting what the next little piece of your voice should sound like, it can instantly spot something that doesn't fit the pattern, like a sudden gust of wind, and just get rid of it. This isn't just theory. It's the engine running behind so much of the clear media we use every single day. So all of this, the statistics, the secret recipes, the goal of minimizing our errors, it all comes together to create a real, practical tool. And this is the hero of our story, the elegant solution we've been building up to. It's called the Wiener filter. This is the name for this whole class of optimum filters, the ones that are designed using all those brilliant principles we just talked about.
They are the workhorses that give us the best possible guess of what a clean signal looks like. Now, figuring out the perfect settings for a Wiener filter involves solving some really complex math called the normal equations. But here's the genius part. What makes this so practical is that some incredibly smart people developed super efficient algorithms, like the Levinson-Durbin algorithm, that can solve these equations in a flash. It takes a really tough math problem and turns it into something our computers can handle easily. And this is the payoff. This chart shows you exactly what happens when a Wiener filter gets to work. The noise level, it plummets. The error rate, it drops right down with it. And the clarity of the signal you actually care about, it shoots way, way up. It's an amazing trade-off that gives us a clean, beautiful result. And just like that, we've come full circle. The next time you're on a phone call in a noisy place and you're amazed at how clear it sounds, or you're watching a beautifully restored old film, you'll know exactly what's going on. It's not magic. It's that digital detective, the Optimum filter, hard at work.
So we've figured out how to find a signal when we have a pretty good idea of its statistical recipe. But that really makes you wonder, doesn't it? What's the next frontier? How do we build filters to find signals and information hidden in data that's so complex we don't even have a recipe for it yet? Well, that's the challenge for the future. Thanks for joining me.